A knowledge of topic 5, which is internal flow, was demonstrated through the following problem, which gives a snake that is vomiting, and we are determined the velocity of the vomit inside the snake's stomach at a Reynolds number of 500 and a Reynolds number of 10,000. To do this, we assume that the flow was steady, that it was constant density, that it was incompressible, there was no work, there was no mass entering the system, that beta equals 1, and there is no entrance or exit effects. First, the Bernoulli equation that includes friction loss was used, and a Reynolds number of 500, which is a laminar, allows us to calculate the F prime number using the equation 16 over the Reynolds number, which is only used for laminar flow. And then the friction loss could be determined after calculating that value. And then that was plugged into this simplified form of the Bernoulli equation to find an equation for V1 that is only in terms of known variables and then an unknown V2. The problem said that we had to use an x-directed momentum balance in order to solve for V2. So after that was done, V2 is found to be this equation and all of those variables are known. So then V2 could be plugged back into the equation for V1 and find a velocity at a Reynolds number of 500 of 3.87 meters per second. Next, the Reynolds number of 10,000 was used, so all steps remain the same except the F prime value will change, and that will change according to this equation, which is the equation for solving for F prime, which is used to find the friction loss for turbulent flow, which is what it is at 10,000 of a Reynolds number. And using that, we were able to find a new velocity of 84.2 meters per second. Based on this information, it can be assumed that a Reynolds number of 500 is more reasonable for what would predict the velocity of vomit inside of a snake's stomach, and even that is likely higher than it would be in real life. So for topic number 7, which is flow through porous media, this is demonstrated through a water flowing through a pipe that is 50% full of donut holes. And to do this, we needed to find the density and the viscosity according to handout 4. And we wanted to find the pressure drop. And we were assuming that there is steady flow, that it's incompressible, that there's no work, and that ambient temperature is 25 degrees Celsius. So to find the pressure drop, we used the Reynolds number for porous media, which is calculated according to the follow equation and was found to be 1,119. Then, using handout 7, the friction factor of 1.8 was found using the curve that was there and the Reynolds number that was determined, and this is plugged back into this equation in order to find the pressure drop. And the pressure drop for this problem was found to be 448.7 pascals. Then to demonstrate topics 6 and 8, which is pump analysis and external fluid flow, we used a system of a fish that is spherically shaped that is swimming towards a pump that is powered by a generator that is pumping water towards it. And to solve this, we need to find the drag coefficient, which is what we're looking for. We need the density and the viscosity of water, which is found in handout 4. For this problem, we assume that there was steady flow, that it was incompressible, that the fish is a sphere, and that the ambient temperature is 95 degrees Celsius and that there's no friction. First, the Bernoulli equation that's including pump work was used, and this was used to solve for the for V2 in the pump, which was 17.32 meters per second. And this is the velocity of the water that is that the fish is swimming directly into. So as given by the problem statement, the fish is swimming at 20.14 meters per second before the pump is turned on, and then that would give us a relative velocity of the fish and the pump of 2.82 meters per second. This value gives us a drag coefficient of 0.416 according to this equation. And in order to see if this is reasonable, the Reynolds number at the velocity that was calculated was found, and that was found to be a turbulent value. And for turbulent flow over a smooth sphere, the drag coefficient is usually a constant 0.44. And since the calculated drag coefficient was 0.416 at a turbulent Reynolds number, this is likely a fairly reasonable calculation. For topic 9, which is compressible flow, we were determining the temperature inside of a man's mouth that is exhaling carbon dioxide at very high temperatures. So to do this, we had to assume that there was an ideal gas, but we're also assuming that the man's mouth is shaped like a nozzle. Compressible flow, steady flow, and constant specific heat at room temperature. Using handout 8, we could find the values for R, Cp, and K, which are used to find the C2. And with a given Mach number in this equation, we could find the velocity of the carbon dioxide leaving the man's mouth, which was 937.7 meters per second. Then an energy balance equation was used, and also the ideal gas assumption was used to say that the change in enthalpy equals Cp delta T. With this information, all variables were known in order to solve for the temperature inside the man's mouth, which was found to be 541 degrees Celsius. For topics 10, 11, and 12, which is all of the Navier-Stokes topics, we used a system of water flowing through an infinitely long vertical cylinder in order to solve for the velocity profile, and then when using numerical methods, the percent difference between the derivative found analytically and then the first derivative numerically using the forward difference formula. To calculate this, we needed to know the density of water and the viscosity of water at 25 degrees Celsius, which was found in handout 4. The assumptions that were made was that the flow was irrotational, that it was steady state, that it was incompressible fluid, that it was a laminar flow, that the fluid was Newtonian, and that the flow was fully developed. The first thing that was done was the continuity equation was used, and it was simplified to find that dv dy equals 0. Then a y component momentum balance was used, and that was simplified to find the following expression. Then that expression was integrated twice in order to find VR. However, VR has two unknown constants that had to be solved. And using the boundary conditions of symmetry, which was at r equals 0, dv dr equals 0, and no slip. So when r equals the total radius of the cylinder, then the velocity, which is at the wall, then the velocity equals 0. Using this, it was found that C1 equals 0, and C2 equals the following expression. Plugging in C1 and C2, we could find that this was the equation for the velocity profile. Then using forward differencing, in this forward differencing formula applied to our system and our variables, we could find, and also using the velocity profile determined here, we could find dv dr between the points of the radius at 0.05 meters and 0.0499 meters. We found that dv dr using forward differencing was equal to negative 274,152 meters per second squared. And then using the equation found here when solving the problem analytically, we could find that dv dr at 0.05 meters was, or at 0.0499 meters was negative 273,878 meters per second squared. The percent difference between those two values was only 0.1%, suggesting that forward differencing is a good approximation for the system at the specified R values.